All right, let's get started. Hi, my name's Ryan Brush. I'm with Cerner out of Kansas City. Thanks for having me to this conference. I've been enjoying a lot of the great sessions so far. Today what I want to talk about is making sense of probably the most complicated data set that I can imagine in healthcare. And we all live pieces of this data set. And every time we go to a doctor, every time we go to a new city, and they don't have that context, they don't have that full medical history to make the informed decisions. We all feel that all the time, day to day. And I want to talk a little bit about the other side of that when you take a look at what the back end of the system looks like. And it actually feels like all our medical records are Humpty Dumpty and they fell off the wall. And we kind of start looking at that with like this sinking feeling. It's like everything's spread out, everything's inconsistent. How do I make sense of this in order to create value, in order to do a better job and help people provide care? And this is a big deal not only for this personal impact on the front end that we all feel all the time, but alarmingly, $1 out of $6 spent on anything in this country is spent on healthcare. And that trend is just, it's been edging up. It's flattened out over the last couple of years, but it's just an enormous amount of money. And even worse, it's not so much the amount of money that's being spent, it's the fact that we're not spending it particularly effectively in a lot of ways. There's a lot of times when there'll be duplicate tests given or unnecessary tests, or worse yet, a potential problem isn't discovered and taken care of because we don't have that complete context of medical data. So this is a big deal. And we told an earlier version of this story in the latest edition of Hadoop, the definitive guide. If you flip to the case study section, we put the page of it there, you can see a little more detail, a little more background. And what I'm going to do today is kind of tell the next few steps of that story that we had told in this book. And when I was putting together this talk, I kind of realized that the structure started to come together in an interesting way. And I found that it really cleanly breaks down into 3 acts that I'm going to go through separately. And well, it's 3 acts mostly. And I think as the convention there is that we're only part of the way through the 3rd act, but maybe as part of this conference and moving forward, we can take those next few steps in this 3rd act of making sense of healthcare. So we'll jump in and we'll talk Act 1. It's making sense of these horrible pieces, putting that picture of Humpty Dumpty back together again. Well, a lot of what it all boils down to, you could express almost everything that I do, everything that we do, in the context of a simple function. It's like we're bringing together all of healthcare data, or as much as we can. We'll go into that, and we ask some question of that, and we provide some answers. So we're just implementing this function, right? And then, of course, it's not that easy, right? Right now in our system, we have some 55 million patients and growing. It's representing about 3 petabytes of data. There's many different code systems. You guys don't need to know what these are, but there's tons of different ways to represent that data. The data sets are incomplete and conflicting. We'll have contradictory information between different data sets as we bring them together. There's no common person identifier. Unlike every other developed nation, basically, in the United States, we don't have a common patient identifier, so we have to figure out if 2 records match. Why would we have a common identifier? We don't need to make things easy, right? This is America. Even when there are standard codes, they're interpreted inconsistently and differently. It's really noisy, and they have different meanings in different contexts. And so this is the challenge that we have before us. It's so important that we can make sense of this so we can do a better job with that $1 out of $6 that we all are spending just in hidden ways so we don't know it. So how do we approach this problem? Well, the good news is that we can apply some techniques that are fairly common and popular in the industry. So one is we can think of it as like a big data processing pipeline, where we're taking a whole bunch of different data sources, whether it's claims or medical records or pharmacy. We can link them together. We can go through a semantic integration phase, which is very deep, of taking all this data and putting it in a way that it's consistent with the other data sets so we can make sense of it. We can apply clinical rules, clinical logic against that to infer new knowledge from that. And by the way, there's always some additional metadata that needs to flow in the system. And then when we expand that out the end, we have a number of applications that sit on the end, like finding registries of common patients with common conditions so we can help engage those people and help them manage their health, as well as doing analytics across the population and then measuring and controlling the quality. Now this picture, this pipeline, is like, I showed it to my colleagues and colleagues at work. I think that maybe they would throw things at me because for every one of these steps in this pipeline, there's a whole bunch of nested stuff that go beneath it. I mean, even just putting together medical records, every one of these has a lot of additional pieces. And this is sort of the pattern, if we step back, of this giant, directed acyclic graph of processing to kind of put these together. So if we look at this model where we're asking a question of all of healthcare and getting an answer, I mean, we can start breaking it down into more discrete pieces. We can start changing from just staring at that huge mess of Humpty Dumpty on the floor and figuring out how to put it together. So we'll do things like, we'll go through some cleaning phase, we'll link these records together based on, and we'll talk about how we do that. We can normalize the structure, and then maybe we can ask the question. So we're going to keep going down, keep going down in this rabbit hole. How do we start making sense of that? One of my favorite things to illustrate some of the complexity dealing with in this space is there's an article in Fortune a year and a half ago or so that talked about how I mentioned how there were 30 different ways just to represent the albumin level in somebody's bloodstream in a medical record. I mean, so albumin is just a type of protein. Like, this is like one thing of many hundreds of tests, and there are 30 distinct ways of making that. And so what we'll do is we need to take all those things and start to reduce that variance. So I usually don't care about the 30 different variations to represent albumin level. I really care, hey, what's your albumin level? And so we can apply clinical knowledge to that. Another thing we can do to rein in this variance is that by looking at the distribution of the input sources, by looking at the nature of the data that we're dealing with, we can draw some inferences for it. A simple example is that if you have we may have a data feed that has temperature. If we don't know if it's an oral temperature or an axillary temperature, the good news is that by virtue of looking at these sheer volumes of data, we can see the difference of distribution of these different data sources and tell, hey, this one is sending us oil, this one is sending us axillary. And so we're starting, the mess is starting to slowly come together, at least for maybe attaching labels to these individual pieces so that we can start to make sense of them, and so we can start to get value from them. And there's many more examples of this that we can go into. But the next step is really, once we kind of start attaching labels to those pieces, well, then we've got to join them together in a big way. And the first thing we have to do is, because being America, we don't have a common patient identifier, is that we have to start linking all these individual pieces. How do I know what to connect to what? How do I put the records of people back together? So we'll take a little look at a little Spark code to do this. I'm using Java code here, and obviously I'm going to be simplifying quite a bit. I'm using Java code just to keep it consistent with some later examples. The Scala code might be a bit more concise, but it looks pretty much the same if you're using Spark. So I might have an RDD of some external record type. And in Spark, an RDD it's an acronym for Resilient Distributed Data Set. It's basically just a big collection of data distributed across a cluster. And let's say these are some external person records. What I want to do is I need to figure out which of these subset of person records are the same person so I can join them together. So basically what we do is we'll do a Cartesian join of everything to everything. Great big data problem, right? A lot of records, need a lot of computational power to do it. And the good news is that these processing models, that Spark and a variety of others, provide a pretty good way to do this. And this actually works. We can do this Cartesian join of everything. Now, once we had that giant Cartesian join, how do we figure out what's linked, what makes sense? Well, what we can do is we can just take our Cartesian record and we can run through a series of transformations through that. So here we'll do a map operation, which just takes every tuple, every fragment of a person to a fragment of a person record to a fragment of a person record, run them through this, and then maybe we'll compute some sort of similarity score between those two. So how do you compute similarity between individual patient records? Well, we tend to have some information tends to be in common, like your name and your social security number, your address. And so if we see two records that have the same social security number and the same name, they'll have a very high score, right? If there's a Bob Smith and a Robert Smith that has the same social security number, we'll link those two together. And we can do pretty good. So you get some sort of score, some sort of confidence that goes with it. And once you have that score of what the confidence is, then we can create a new record that indicates, hey, this is the similarity between these two records. We create it and we emit it. And that's that map operation. We've transformed that data set from all these raw fragments of information into something that indicates, hey, there's some indication of similarity. But of course, we're really only interested in people that are actually the same. And so we can just take their similarity score, filter it based on some threshold, and then we have these links. We've connected those individual fragments, and so we're making progress. And you kind of think, of this operation as building this giant table for everyone in some particular area, and on each axis, what is their confidence that they're the same person? I mean, if it's the same record, our score should be 1, right? Because they're identical. But in each one of these, we can be more confident that person 1 and person 2 are the same because they had the same score. And so, I mean, these pieces are coming together. We know what pieces to attach. And so the next step is that we want to reassemble Humpty Dumpty in code. And this is where we start getting even more interesting. So back to our little simplified Scala example. Let's say that we have, that first one is the IDs, the IDs to link together. So each pair is a tuple of one person identifier and another person identifier. And the bottom one is the tuple of the person identifier in the record itself. Well, I mean, the nice thing is that we can, Spark offers some really nice operations. You can just basically do a join from one data set to another data set, which basically just unifies the first item of those two keys. We can do a map operation from these, group them together, and then run an arbitrary function to merge all these records. I mean, there's a lot more depth to going into this, but the nice thing is that when you're thinking in this world of, you have all these huge data sets, you can kind of start breaking it down into these simple transformative steps in order to get back to, this sort of unified view of this transformation. This kind of gives you an idea of sort of the structure of the pipeline and how we can codify it in something like Spark. And it works pretty well. The challenge that is the magic, the hand waving behind, I have merge external records, right? I mean, we were talking about how complex the data is. And what kind of approaches can we use? How can we start boiling down that really ugly problem of dealing with those external records? And so if you look at some of this, and I don't expect anyone to make sense of this unless you happen to be a terminologist or have been one in your past life. It's we have data that looks like this. We'll have all these different coding systems that mean all kinds of different things. And I couldn't even tell you what these are looking at it. So how do you go about making sense? How do I get value out of such noisy, complicated data sets? Well, the approach that we've taken is that we can start organizing that, and then we can use, we'll use rule-based transformations. So we can map, these particular items, that means these indicate this person is on an insulin medication by either having these simple codified mapping or actually having explicit if-then rules built into our system. The next one might indicate, hey, this one's a diabetes condition. And then we could project it on to they're a diabetic. And this kind of a pattern that we tend to follow when we start applying our logic over this complex clinical data. Sort of the phrase that we've been used, I think it goes back to even some of the old Gang of Four books. It's code in the language of the domain, right? The language of the domain of people trying to make sense of the system is insulin medication or diabetes condition or is diabetic. It's not, SNOMED, 3.8, et cetera, et cetera. So we can project our complex data sets into the language of the domain, write our logic in that language, which becomes a lot easier to understand the logic and as a way to share and understand requirements with the clinical experts that are trying to work with this system. And if you're curious about some of the deeper techniques and approaches, and I don't have time in this talk to go super deep into that, I gave a talk a year and a half ago at Strange Loop about a rules-based approach to make sense of healthcare data. If you just Google retaking rules for basically the string at the bottom, you'll find the YouTube video of that talk, which was a fun talk to give in itself. But really, this pattern, it's reminiscent of something else from another industry. Actually, not another industry, but just another endeavor entirely. And it reminds me of, I occasionally like to play chess, and I'm not a very good player, but it reminds me of this in that if you talk to a great chess player, a master level chess player, this person, he or she doesn't think in terms of individual pieces. She thinks in terms of the structures, the formations that live on the board, and the patterns that tend to emerge in those formations. So I'll lose to a good chess player, not because this person has a dramatically higher working memory than I do or can dramatically fit that many more pieces in his or her head than I can, but because this person is literally thinking at a higher level of abstraction when dealing with a problem. And it's similar, I think, in healthcare. we don't want your engineers or your clinicians, your domain experts, to be not thinking in terms of those codes, have them thinking in these higher level pieces. And we can be a lot more successful like that by putting that in that language of the domain, if you will. And once you have that in that language, the nice thing is there's some nice properties that tend to emerge after that. One of which is that you can transform this model that they're using into some other structure that's specific that fits their use case very well. So if I have a domain, I can project it on a tabular model where I might have some person identifiers, and I can have, every clinical result can be a column. So rather than a concept level, I look at a BMI column or an albumin level column and so on and so forth, which really lends itself to using from a variety of tools. I mean, we have a bunch of people that love using R, so we can just tap into this and immediately, just in that tabular format, they're immediately productive. And whether it's R, or whether it's SAS, whether it's Spark MLlib, just projecting your data into a simple model that's usable, a simple tabular model, really opens up to a lot of use cases. And I kind of think about kind of classifying that pattern, the way that we kind of model it, is that I like to think of it as start with the question you want to ask and model your data to fit that question. And so that tabular model makes a lot of sense if I'm doing something, if I want to ask questions, say, in the context of an R console or a Spark MLlib, because all my features are right there. The user of that console can immediately go through, use those features, explore it, and do so very quickly because we've taken this tremendous computational power and applied it to put our data in a way that helps us ask the questions that we want to ask. So that's a step, right? I mean, we've made some progress. Things go pretty well so far. But there's still a lot more challenges that we experience in this space. One of which is that it's not always clear, what are the questions that we want to be asking. So if we oftentimes we're provided a problem with, we want to improve the care of diabetics in this particular population. Sometimes we want to identify what our biggest expenditures are, but then once we figure that out, who's at risk, how do we help manage, what's the most important things that we can do? So it's this big, hairy problem that we're dealing with in some spaces. And we have some tools to help us get all the way there, but it's not always clear what the best path is to solve these problems. And there's, of course, huge variance in different conditions and different problems that we're trying to face. And I think that we can draw a lesson here that's actually a few decades old now, and that I'm not sure if anyone know it. This goes back to the story of one of my favorite engineering stories of all time, and that is attempts to build a human-powered airplane. And there was actually a competition. There was a prize associated with building a human-powered airplane. So a number of attempts were made at it, and they weren't going very well for the most part. What would happen is that somebody would make an attempt, they build a plane, and they would take off or want to get off the ground, and if it did, it would crash immediately and break into pieces. And okay, back to the drawing board. A year later, they built another plane. Maybe it got a little bit higher and crashed, broke into pieces. A year later, another one. So there wasn't much progress being made in this space. And that's the way it went for several years until a well-known aerospace engineer, Paul MacCready, came in and he looked at the problem. And I think he had possibly one of my favorite single greatest insights in all of engineering, and that is that the problem is we don't understand the problem. And so what Paul MacCready did is he took this, rather than attempting to build an airplane that a human could fly, what he did is took an airplane that you could put back together in a day. And so the first attempt failed, but then they put it together a slightly different way. The second attempt failed, and again and again and again, until eventually they were actually successful in using that approach. And they actually ended up winning the prize. I should give a hat tip to my friend Josh Wills, who was the first person that introduced this model to me, because I think this is a really effective way to think about how we can attack this problem. And I think that this is also doubly effective if you're working in this space of what we conventionally consider big data. Because today we're bringing all together this data into all these huge systems with enormous computational power. And so what can we do? We can take it, we can reprocess our data again and again and again. If something doesn't work, we transform it to a new model. We can transform data to many different models to meet many different needs. And if something doesn't work, we throw out that model and we reproduce it from our raw data. The key is that we can iterate more quickly than we could with another approach, with another technology. No longer are we in this world of having to go requisition servers to spin up, a new data cube, right? It's just there. We can apply it, we can transform it. And this sort of quick iterations is essential to make sense of a data set as complex as healthcare, and probably with a whole lot of other data sets as well. I mean, if there's one thing that I think that we want to remember, it's just the problem is we don't understand the problem and find a way to iteratively move towards that. So our function is starting to grow a little bit like this. We'll clean the data, we'll create these for-purpose projections to make sense of them. We can ask questions of that. And this approach is actually, it's working. It's working pretty well for a number of areas. There's one for our ability to predict sepsis. This one was pretty cool. By using pretty much the techniques that we just described, we built a sepsis model. We iterated on it very heavily, and we have what we believe is possibly one of the better, if not the best, models to predict sepsis that there is. Now, I know you can't read this. This is kind of like to illustrate the concept of the model. And even one of our clients actually told us, after the first year that we had this in production, they estimated that we saved 500 some lives by deploying the sepsis model. This is a large healthcare institution. And that's pretty neat. The fact that we can take this approach, that we can understand that we didn't understand the problem, and that we can iterate towards it to get something that provides some real value. That's tremendous. I love doing that sort of thing. And we're starting to apply it in a number of other ways. One of the big things in healthcare is we'll throw out the terms like population health management. It's like there's increasing pressure in order to offer better quality care and at lower costs. Increasingly healthcare systems, rather than just being a fee-for-service model in which you're perversely paid more the sicker your patients are, will have these value-based models in which we actually have a strong incentive throughout the healthcare system in order to control costs. And this is a tool that can help with that, and that we can identify those risks and help bring those costs down. And you can imagine that there's a number of other things that can hang off of this approach for making sense of data. And I think that everything I've talked through so far, is pretty general to a lot of other industries. So far so good. And I think that we can take just one moment here and look at some of the early lessons. That are some of the things that we've learned by going through all these efforts to work with this data. The first thing that I want to put out is that make no assumptions about your incoming data. One mistake that we made early on is that you'd think that there was some reasonable upper bound on the size of a medical record, right? Maybe it's dozens of gigabytes or whatever, but I think that there'd be some reasonable upper bound. And we had processing points in which we were constrained to some reasonable upper bound. Now, it turns out that even though logically that is the case, if you're dealing with 55 million different patient records from all these different feeds, we found instances in which somebody was there'd be instances in which a particular hospital might have had a test patient that they used to test all of their device feeds, and so they just put all of this medical history, many gigabytes onto this individual patient record, which once we made it through into our system, and then things started breaking. And so you really have to make, even in this case, if you can detect this isn't really a valid record, you can blacklist it and not process it. But you really can't make any assumptions, because any type of noise or invalid data, when you scale up, eventually you're going to reach it. And as you scale up and you start seeing those errors, the other lesson that we found early on is that your errors are a signal. In that a lot of times when we do development process, something goes wrong, we throw an exception, it gets written out to a log, and maybe we have some sort of operations tooling, maybe it shows up in Splunk or something like that. We can analyze it, and that's great in most cases. But if you're dealing with many tens of millions of medical records and hundreds of billions of data elements, all of which can be flawed, or all of which could expose some bug in your code, it's not really something, it becomes much less tractable to go through and dig through individual log messages. And then also, oftentimes, the incoming data source may be malformed in some way, so it's not a bug in your code at all. So what we've done is that since viewing the errors of the signal rather than in many cases writing them out to a log, what we'll do is if we can catch it and we believe that there is some sort of data problem, we actually write that separate data out into like a separate data set itself. So we can query, we can see, from this particular data source, they're sending us a bunch of code values that we don't recognize. Or we're seeing this high percentage of malformed records from this, and we can actually use something like a Hive to query on that information to make sense of it. And so you have to tap into that, and it's more than just analyze then post after the fact log analysis. This is just a core part of your system. And then another thing that we've learned is that when bringing all together all these data sources, I mean there's often many steps and many convoluted ETL practices along the way, and we have to be aware of the signature of these data sources. And by that I mean a given data source will probably have, it'll have its peaks and troughs of data that it loads. It'll have a certain distribution of data that it'll send to the system. And we need to be able to detect if something goes wrong with that feed, and we need to be able to detect it quickly because this is a pretty critical system. And so the good news is that we can actually find, if you can actually detect if there's a significant change in the signature, if you're not getting a particular type of result, or you're getting a dramatic drop of volume, or an increase of volume could indicate some sort of misconfiguration. We can go that and quickly investigate those data sources. This is actually something that we want to continue to be improved. I mean, something like you can use an intrusion detection algorithm or a k-means algorithm or something like that to kind of understand how to dig into this. So there's a couple things that got us going so far. And like I said, this is working fairly well. But the latency, right, for the approach that I've talked so far, and the complexity of the pipeline that we're doing gets pretty involved. And that leads us to Act 2. We want to put together healthcare fast. I mean, for many of our problems, a MapReduce job or something like that that's run, or a batch job that's run at some interval, maybe a couple times a day, is sufficient. But a lot of things, it's not. There's really need to reduce that latency. So how do we take everything that we described at this point and turn it into a world in which we can dramatically reduce that? We can go from hours to minutes or even seconds. So let's take that look at that example that we had earlier. This is the same code I had before, where we have a couple RDDs, we're joining them together, we're doing a group in that transformation. So how do we get this into a streaming model? And Spark offers streaming. So let's take a look at what it takes to move over to that. Well, the first thing is that we'll switch from an RDD, that resilient distributed data set, to a stream of RDDs, which is called a D-stream. And all this is just, Spark, a number of you are sure aware, uses what's called a micro-batch approach, and that you just have a series of RDDs, and that's how it kind of simulates a real-time processing. That series is just a D-stream. So we'll have our D-stream of these external records, and we'll have D-stream of our links of patients that connect to one another. And then maybe we can join them together. But the catch is that, well, if you attempt to join them together, that's not quite what you want. Because the join operation in Spark streaming, what it really does is actually only joins the RDDs that are in the same window in a D stream, is the same one that live together. And so what we really have to start doing is doing a much more involved stateful computation, where we'll catch something that's called a state spec. And really what that is it's just a rolling aggregation of functions that we can create, and we can apply that. And all this is getting a little bit involved. So I think it's a little bit easier to actually look at a depiction of it. And so this is basically how we can do a real-time processing in the Spark streaming type of setting, where we'll have our links, our updates to our links, our updates to our records, and then combine them together in some way, merge them with some previous state. And so as every time I get some new data element that I want to add to the context to a person record that I've already had, I can merge that in, and then I can emit that state downstream to do all those rules. And this is doable. You can take at least the functions. You can do all this in Spark streaming, and all this is achievable. What's interesting is that we found a couple of cases where I think maybe we have some specific problems that add a great deal of complexity to that. And the first one comes to mind is what about a delete of a data set? Or what about an unlink of a data set? And oftentimes when we look at these streaming models, we're just thinking in terms of some aggregation, like I'm aggregating logs or I'm aggregating counters, and where there is no such thing as of two things that can be unlinked. In that case, you're fine. But if you have a delete, what happens downstream is that if I unlink two parts of a person record, then everything downstream that has to do it has to be unlinked as well. Every report, every query has to be unlinked as well. So we have to propagate this change information all the way downstream, and it kind of permeates through all of our code. It gets really complicated. And so the first lesson here is like stream processing. You can't think of stream processing as sort of a fast batch processing. I mean, the pipelines have different semantics. There's not a lot of reuse beyond the core functions because you have to write those rolling aggregations and you have to implement that compensation logic when two things get unlinked. You have to make sure that you remove them downstream. And really the model that's used in a lot of processing frameworks that used in Spark and a lot of others it looks like this, is where you have a batch processing model and you have a stream processing model. And in the middle, it's like there's a bit of reusable code in that you can reuse your transformation functions, but you can't really use your join operations or your aggregations or any of that stuff. So you're really writing two pipelines. Even if you're using Spark and Spark Streaming, you're really writing two pipelines to deal with that. And that adds, which adds some overhead to the system. So we were working through this class of problem, and we're trying to figure out a way to go forward. And one insight that we thought was kind of useful was what John Carmack said in a completely unrelated space, is that if you're willing to give up some flexibility, you can usually do something better. And that applies to us in that we didn't actually need the full expressiveness of Spark for our particular data set that we were doing. So what we could do is we could take advantage of something, just the nature of the processing that we're doing, to actually build a simple API on top of Spark that could be deployed both in a batch and a streaming model. And it kind of looked, it looked a little bit like this, where, to avoid confusion, I'll call it like a rolling map of things flowing into the system and a rolling reduce, which, by themselves, these look pretty much like a map and reduce function. Everything's identified by some key and some version, because we can have data coming in out of order, so we need to make sure we clean up the right version. The only difference is that for the emitter, we could emit some result from our map functions and our reduce functions, or in this case where we need to clean up some form of outdated state. If something was no longer relevant, then we could emit what we call a tombstone, basically a marker saying, hey, this particular link between these two people is no longer valid, or this particular data element is no longer valid, and that sends downstream. So our programming model evolved. It became basically something like this, where by taking advantage of just the nature of the domain that we're working, we just built this domain-specific API. We're able to write mostly reusable pipelines on top of it, so we didn't have to have all this duplicate logic between our batch mode and our streaming mode. And this is okay, right? This worked. But you have to ask, well, are we done yet? Are we declared victory? Have we solved our data processing problems? And I guess you can figure out the answer to that. It's like, no, it's limited in its expressiveness. There's artificial complexity in having to track this tombstone state down the system. It's not really composable in that I can't plug it into other units of computation or other frameworks. There's an artificial learning curve, because suddenly I can't just, I can't learn an open source processing framework. I have to learn this, proprietary model, this API that lives on top of it. And so this was kind of, we've kind of gotten to this spot where we really wanted to find a better path forward to address these shortcomings that we were dealing with. And this leads us into Act 3, and where we've started to reframe the problem to make sense. Because historically, we would think of things as just this, what we showed before. There was batch, there was stream, and there was some reusable code in beneath. But in reality, it's like, this is really a much better model, right? And if you think about it, batch processing really is a subset of stream processing. There's nothing that I can do in batch logically that I can't do in a streaming mode. It's just I process everything in one go. And this idea was first proposed, the first time I saw it was that Jay Krebs wrote a nice piece and labeled this the Kappa architecture, in which if I want to reprocess my entire history, I can just replay the entire queue of changes that run through the system. And this is really based on this log-based model. There was a great talk about Kafka actually in this room a couple sessions ago that went into more in depth, and that makes sense. And so this is kind of cool, right? And so we're thinking, yeah, let's make everything a stream, right? And if everything's a stream, then we can run both stream and batch model. It's a subset of it, and that's great. But even then, I think this is a step forward. And honestly, if your problem can be expressed in a way where you view everything as a stream and you're able to do so, then absolutely do that, because I think that makes things a lot simpler. But what we found is that it gets harder if your data elements can't be expressed as what are called monoids, and know a number of you know what those are, but really monowit is just, it's just a function an associative function. So things like I can do adding totals together or adding things to a list or grouping things together. This works really well in a stream-based world, but things that aren't a monowit are things like what we were dealing with, in which you could unlink and had to maintain and propagate that delete state downstream. So there's still that complexity of managing how things were unattached and propagating that state. So this is a time when viewing everything as a stream may be a challenge. And then I think that the technology is once you'll reach a certain data volume in which maybe we're not quite up to the task. Like I said, we have about 3 petabytes of data. And maybe we'll get to the point where we can land 3 petabytes on a queue, and on a distributed queue, obviously, and reprocess all of that. Maybe that'll happen, but I don't think we're quite there yet. So we weren't quite able to jump into this perspective and make everything a stream, although I think for a lot of problems, it's a great idea. So we're looking for another path forward, and then we ran across this paper this research paper from Google for a project that's now called Apache Beam. And Beam is the name that they wanted to unify batch and stream. And this is kind of exciting because for what kind of Beam is the way I view it is it's potentially like a POSIX type API for data processing, and that it's an API. And this API has multiple different implementations on which you can run it. You can run it on Spark, you can run it on Flink, which is a talk earlier today, and you can run it on Google's Cloud Dataflow system. So it provides a nice API with multiple runners. It provides composable units, so I can just write my logic as these P transforms or parallel transforms, and you can build on top of that. And it unifies batches. And it really offers a unification of these batch and stream models. And we're going to look at kind of how it does that and how we think that it can help solve the type of problems that we're dealing with. So we have to introduce a couple concepts when working with this cloud data, or this Apache Beam / originally Google's Cloud Dataflow model. And then rather than batch and stream and batch data sets, we're starting to think of bounded data sets, where a bound is just a fixed data set, a fixed size. And an unbounded data set is something that's just continuously updating. So something that can have new data append to it, while your process is running. And we're going to show how we use these. And then whether you have an unbounded or a bounded or unbounded data set, you can process some window of that data set, which is just a time range of your data. This is referred to as event time. It's typically focused on like event type data. So the window is the time rate of the data that you want to process at some. And then a trigger is, when do I process that data? So window is like, what data do I want to process? Trigger is like, when do I want to actually fire the processing? So if we look at how we can think about this, if I just want to say have a batch model where I process all of my historical data, my window might be all of history, and then my trigger could be some point in time after I've gotten everything that I'm interested in. If I'm interested in doing like hourly updates, for instance, my windows might be along each one of those hours. And then my triggers are simply just, some point after I land that, I trigger my processing for each one of those. And if I want to do like rolling hourly updates, then again, my windows, I just have different windows and different triggers. So you can see like a huge number of processing models can be expressed using this. Another one, if I want to do something like emit preliminary updates, let's say I have hourly windows. But if I want to, before each hour is done, I want to have like preliminary results for that window. If I'm taking some sort of score, something like that, I can just have triggers that fire multiple times in the window and then fire results after the window's finished, which will be the final value. And so all of these like different kind of processing modes can be expressed. And then of course the time interval for hourly, that's completely arbitrary. You can have it arbitrarily short. So maybe here you have a minute and you fire every 15 seconds or something like that. And you can shrink that down. And how fast you shrink it down is really just a function of how much resources you want to throw at this problem to reduce your latency. And so the nice thing is like we've kind of taken this model where batch and stream are unified, and we can describe either operations using these primitives. So let's take a look at how we might code it. Well, there's really 2 steps to that. The first one is we're going to build our transformation of the data, and then the second step is we're going to apply our windowing and our triggering semantics to that, which I think is really important because this allows us to decouple. I can run my transformation once, and I can decide what sort of windows. Do I want it run over all of history, or do I want it run every 5 minutes? I can decide that independently of my transformation. So to implement a transformation using the Apache Beam model is I just implement this thing called a P transform. Well, I have a couple things here. These aren't super important, but they're basically tags for the input that I use. And then I really just need to implement, these tags are like handles for the input that I use. And then I just implement this apply function where I take some sort of input, in this case a p collection tuple, which is just a couple p collections that I want to join. I do some transformation and I get my glorious person record that I can do things with. So how do we implement this apply function? Now there's just a couple steps that we can do with it. The first thing that we'll do is we'll use those tuple keys to build a key value that's co-grouped. Actually, I'm sorry, apply that there. So we'll use those two tuple keys. We'll get the data sets we want to link together, and then we'll apply the co-group by key, which guess what? That's just another p-transform. Like everything in this model is just p-transforms, and some are primitives, like a co-group operation that's provided by the API, and some are composites, like whatever arbitrary domain-specific transformation you want to have. But everything is a p-transform that you apply to a collection or a tuple of collections. So once we have this co-grouped item, then what we can do is we can run this link external records function, which basically similar logic to what we had done before, and then go through these similar steps where we combine all the data and emit it. And the specifics of these aren't super important, but it's just this pattern. If I have like a composite transform, I'm building it up of nested transforms to emit the data that I want. And nothing in my transform cares whether it's batch, it doesn't care whether it's streaming, it doesn't care about if I'm running all of history or if I'm running 10 seconds of history. These are completely independent. So now, but at some point we have to decide what we do want to run over. And so we'll look at this logic of how we invoke the transform. So we'll have a collection of these record links to tie things together. We'll have one of these external records. And then this is how we can call that linked record transform that we did. We use the tuples, and then we just apply that transform that we wrote. And the outcome is that p collection of people that we're going for. So again, same pattern, just transforms applied. But what we left out here is that we still have to define what data are we processing, what are our windows and triggers. So the simplest one is, let's say if I just want to process everything that lives in an hour. In our use case, this doesn't make a lot of sense because you usually want to merge with the whole history. But if I did want that approach, I can just say, hey, for my collection of links, I'm just going to window that into an hour of fixed windows of an hour, and that's the p collection. I can pass that in to my transform that exists, and then join it from there. So let's say I wanted to allow late data to enter into the system. So I can just say with allowed lateness, and that way if anything shows up to 15 minutes late, I just included the data set, and then I fire my activation. And accumulating fired panes, I'll reference the documentation for that, but that basically means it keeps any previous results that were fired is merged into the new results. You can also discard previous results for certain use cases when it makes sense. And there's a lot of different, and then finally, let's say if I wanted to do something where I fired preliminary results, I can add triggering, so after the start of that first element, plus a delay of 10 minutes. So basically I just took that same logic and now it'll fire preliminary results every 10 minutes. And I didn't change my transformation, I didn't change any of my other code. I just basically declared in this logic what subset data I'm interested in. And then if you want to do that sliding windows example, there's different ones. So there's a sliding window of 120 minutes. The same thing. I just kind of changed that, and everything is taken care of behind the scenes for me. So let's look at what we probably actually want to do, which is merge all of history. Well, we can window into a global window, which is everything. But obviously the end, the global window applies like to the end of time. We can't just wait till the end of time to process everything. So what we need to do is we need to trigger computation of that all of time global window at some period. So we can add a trigger for it. So after some element shows up, plus some delay of 5 minutes, and then we'll accumulate the panes so we're always sending out the latest results. So like we've shown many different permutations of processing models that can work in what we consider a batch and streaming model, and just have to declare it with how we invoke this transformation. And this is exciting to me because there's a lot of concerns that tend to get tangled up. We have to deal with what data I've received, when should I process it, how should I group the data, process it, what if I want to eliminate, if I emit preliminary results, how should I amend those preliminary results? So there's just these tons of questions that you have to make. And when we're trying to build these things, historically in most processing models, it's been really painful, because what we've had to do is we've had to kind of merge them. All that stuff tends to get mixed in with all the code and blended together. And this actually reminds me a bit of a talk that Rich Hickey gave a few years ago at Strange Loop, in that this is actually a thing that people do, but apparently there's a woven castle in which people will knit these castles together, and then there's a Lego castle, which we're probably more familiar with. And in the woven castle, it's like, what do I do? It's like, I can't change that. I can't change a turret, or I can't swap out any pieces of it and do something else with it. It's really what it is, and it's stuck in that state, because all of my concerns are tightly intermingled together. Whereas in a Lego castle, I can do whatever I want. I can add a new turret, I can do any piece in there. And I feel like this is a big step forward with regards to how we approach scalable data processing, to how we make sense of these really big, complicated data sets, is to start separating these concerns. And I think that the Beam programming models is a pretty nice step forward. Now, I should add some caveats to that, in that some of the things that we're dependent on, Beam is raw. It's like a 0.1. It's based on the Google Dataflow approach, which has a very scalable implementation. So if you just basically want to use it in Google's cloud, you can. Some of the retraction logic that we need to depend on to clean up incorrect, out-of-date results are still in implementation. And the runners are at a varying level of maturity. The Flink runner is actually quite mature, and of course the Google Cloud Dataflow runner is solid. The Spark runner is lagging behind a bit. And the API is still subject to change, being such an early release. And I also want to say is that Spark offers a really rich ecosystem independently of this, in terms of MLlib and Spark SQL, and there's a nice REPL experience. There's tons of things that are awesome about Spark that don't exist in like a Dataflow type ecosystem. But I think that what is exposing is that we're dealing with a couple different classes of problems. There's one of these really large, complex, nasty data processing pipelines. You can kind of live in the space that we're working with in healthcare. And then there's this sort of more interactive, hands-on exploration and transformation of data that we're dealing with. And I think that Spark is really good at the exploration and transformation of the data, but I'd love to see more of these ideas sort of converge into a common processing infrastructure, because I think they're both really important about these systems. So anyway, back to our depiction of how are we doing so far? And I feel like we've gone from staring at Humpty Dumpty with this sort of sinking feeling of like, where do I begin? How do I approach this problem? To we've broken it down to, from this absolute mystery of where do I begin, to like a set of solvable problems that can be approached independently. I don't think we have all the answers yet. And it'll be interesting to see how Apache Beam evolves and how other projects incorporate ideas that are going on. So we haven't reached, I think it's too early to say that something like the Lambda architecture is dead. I do feel like we've chopped off a number of years off the lifetime of the Lambda architecture, because this offers such a much better programming experience. And I think it allows for engines to iteratively improve underneath the development model. And so I feel really good that we're headed down the right path. That we're starting to move the conversation from batch versus streaming to like a common model that leads underneath it. But ultimately, I think the story is really, it's a confluence of a larger story that tends to happen with technologies. Like over time, we build a better understanding. We first start out, we're just trying to figure out what is this problem space that we're dealing with. Then we start to discover patterns in that. And then after we discover patterns, we start building these really nice prescriptive libraries that codify the best practices of how to do things. If any of you guys did web development 10, 15 years ago, it was a mess, right? Everyone was just writing their own state management and security. Like everything was just a one-off and an exercise to the user. But now it's like modern web frameworks are actually pretty nice. If you use one of these APIs, you're going to have something that's okay. You're going to have something that's pretty good, because we have this prescriptive model for how to build this class of system. And when we first started building this, when I first started working in the Hadoop space, I really felt like we were way down here. It's like, yeah, things were possible. We could do all these things, but there's a tremendous noise, and we felt like we were having to solve these really hard problems that had absolutely nothing to do with the business value that we were wanting to provide. And the good news is that I feel like we're just now maybe taking that step over from this sort of pattern discovery into a prescriptive framework that can solve all these batch and real-time things in a way that works. And that's exciting, because it really allows us to focus on the essence of the problems. I want to be focusing on healthcare, on making things better there, rather than the accidents, rather than thinking about how do I juggle all these different these programming models, the accidents in the sense that Fred Brooks was thinking. And this itself, I think, is a big step forward, and hopefully can apply to a lot of domains. So with that, thank you for your time, and I think we look like I have some time for questions.
So throughout the talk, you kind of went through, started with Hadoop, right, in the 4th edition, your use case, then you went to Spark, now you're using the Google Dataflow or Apache Beam.
Yeah.
Is that the progression? So are you now mostly Apache Beam, and that's what you're excited about, or are you still using Spark?
So so we're, like I said, we're part of the way through the third part of the story. So basically what we've done so far is we built a prototype using the Apache Beam programming model to see if it is sufficiently expressive to meet the problems that we have. So we have not taken Beam to production yet. I mean, I'm not sure if I couldn't give you insights on like the operational characteristics or anything. What I am confident about is like this programming model is a big step forward. And the nice thing is, since Beam is an API with multiple implementations, and conceivably you could pick an implementation that fits your workload better. So like I said, we're halfway through. We're part of the way through the chapter. The third part.
So in Prod, you're still vanilla Spark.
Yeah, I mean we're. Yeah. So, I think there was a question in the back there.
So I was just a little unclear. In terms of handling the updating of old bad links or the tombstone problem, is that all handled by Beam, or that's all covered in this retractions that isn't done yet? Or
so it is the retractions that handles that old state, and it turns out you only have to retract like in certain specific circumstances. And it gets really involved really quickly, but basically every time if I omit something, and if I'm just doing like map operations, then I can just rerun that sequence of map operations. But if I'm regrouping data by different keys, then I have to basically rerun that new group of data, which is the flow that the Beam programming model handles, even though it's not implemented. So the answer is that yes, the retraction model is being built into Beam handles that or eliminates the need for doing the tombstoning stuff. And there's a lot more details in the Google Cloud Dataflow paper if you're really interested in going deep in that. But it's a tough space.
So in terms of the data that you get, do you have a lot of, when you're talking about retractions, do you mean like something changed and is no longer true, and you're always providing a current snapshot of a patient, or do you have like a historical, it's like, hey, well, they were sick, now they're better, now they're sick again?
No, if something that changes, when something that changed that's no longer true. So like an instance, the example that we used here is we'll in the metaphor of putting Humpty Dumpty back together again, we're linking multiple person records, right? Sometimes those links are incorrect. Two things were linked together, it's flawed, we got bad, sometimes like information was assigned to the wrong person, which is terrifying, but it actually happens. So we basically need to undo that connection between records, and make it so and expunge it from any downstream report. So that's the main thing that happens. And variations of that, like if the wrong information is associated with a person to retract that, which hopefully doesn't happen hardly at all. But when you're dealing at this scale, you have to be able to handle with any of those noisy edge cases. Thanks. Sure thing.
Just a quick question, because you mentioned latency and petabyte scale. How do you deal with, you just write the code out there, oh, map, reduce, keep going. But this has to run on actual hardware, on actual data sets. What kind of troubles did you guys run into kind of meeting deadlines, and what you did to kind of like meet those deadlines?
Yeah. So the multi-petabyte, that's the amount of data that's, kind of at rest in the system. So we're not like trying to do petabytes, of ingestion a day or anything like that. Although, when we're bringing on, a larger client, we'll see many terabytes of data flowing into the system. And it's like, I think that our main production node, we have like an 800 node Hadoop cluster that's able to, for the most part, keep up with that. I'm not deeply on the operations side, but I know we have some folks that have to be very involved in keeping all those things going. And like I said, we're not actually, that isn't Beam yet. So hopefully it will be at some point. All right. Any other questions? Let's go. Okay, great. Well, thank you very much.